Well, good morning, everyone. I'm so glad you're able to join us today. And I'm just going to try to do this in one take. So if something weird happens, you'll see it. And I'm not going to try to do anything necessarily to cover it up. We're not going to edit any of this. So this is just the way it's going to be. Okay, so you've done your experiment. And hopefully everything worked out well. So you should have a better understanding now of the mass spring system. And there's just a couple of things before we go into this last part of the module. I just want to make sure I remind you of a couple of things first. Back on page 328, there are those four statements in bold, and it's talking about a mass spring system. Now I'm just going to use one of the springs here that I got, and possibility using in the experiment. Maximum acceleration is when it's at this point, so its amplitude is greatest and so this is the maximum point of acceleration. The maximum speed is occurring once it comes back to equilibrium. Okay? And acceleration though is zero at this point. So this is where I'm sorry. The acceleration is zero at this point, so the speed is maximum, but acceleration is zero. And then at this point, at amplitude, the speed is zero, but the acceleration is greatest. So just wanted to go through and remind you of those concepts before we move on. I believe we left off on page 334, and we were talking about displacement from equilibrium. We had looked at that graph, figure 10.2, and where you're able to measure both the potential energy and the kinetic energy in this kind of a system. Yeah, I had a timer here and I forgot to start it. Well, there you go. We're going already. I think there's a timer on here somewhere. Okay, a minute 50 seconds. Oh, a little behind. And we also, I think, had talked through the two statements in bold at the bottom of 334. At the amplitude of its motion, a mass spring system has no kinetic energy. So if we go back to this example, at this point, there's no kinetic energy. It's all potential energy. And at this point, it's all kinetic energy and no potential energy. So we're going to be able to measure the kinetic energy or potential energy at almost any point in between. And that's part of what the problems that are coming up will be asking, is if you have a system whose amplitude is this far, but it's 2.5 centimeters past that, or 2.5 centimeters from the original distance, what's its kinetic energy or what's its speed? And so there's ways to accomplish that, and that's because you can know that at amplitude, all of the energy is potential, but at equilibrium, all of the energy is kinetic. And we can utilize that. If you look back over to 335, they give you equation 1012. So potential energy, you can use the K or the spring constant. Potential energy equals 1/2 times K times the square of the displacement. So that's a way so at the point where things are spread furthest apart, and this thing keeps falling apart. So at amplitude, it's all potential energy, and it's equal to that. So if you know the spring constant, if you know the displacement, you'll be able to calculate the potential energy that's available. And if you remember from Module 8, the next equation down there on 335 is for kinetic energy, 1/2 times mass times the velocity squared. So, but again, the sum of the kinetic energy plus the potential energy always equals the total energy, which never changes. So the total energy never changes. So at amplitude, the total energy is equal to the potential energy, and at equilibrium, the total energy is equal to the maximum kinetic energy at that point. So, so he gives you an illustration of that. The next equation, 1013 on 335. Kinetic energy of the mass spring system plus the potential energy. Now you can put that equal to 1/2 times K times the amplitude squared. Because 1/2 times K times the amplitude squared is the total energy of the system. So, so now you can use these three equations in analyzing the motion of a mass in a spring. And so he starts with example 10.4, and it says, in stretching an 11.2 kilogram mass on a spring, a physicist does 35 joules of work. So what he's saying is that in order to display, he puts the mass, and he does 35 joules of work. So he spent 35 joules of work to get it to an amplitude that we don't know yet, but we know how much energy he used or how much work he did to accomplish that. So that says, it asks you, what is the spring constant? If this work stretches the spring 14.1 centimeters. So you've got your spring, he does 35 joules of work, and it lengthens 14.1 centimeters. So the question is then, how do we find out what the value of K is? And then he says, if the spring were let go, what is the maximum kinetic energy it could have? And what speed would the mass have at that point? Well, with the three equations above, you have everything you need to answer all three of those questions. So he shows you an example, potential energy equals 1/2 times K times delta X squared. And he simply plugs the numbers he's got into that. So the amplitude, 0.141 meters and 35 joules. You can solve for K. You get 3.5 times 10 to the third newtons per meter. So that now is the value of K. And now that you know the value of K, you're able to see, as he throws you below, kinetic energy plus potential energy equals 1/2 times K times the amplitude. Well, now you know K, you know the amplitude, and at that point, at equilibrium, when the speed is greatest, potential energy is 0. So you can take the potential energy out. So kinetic energy equals 35 newtons times meter, which is actually 35 joules. So finally now that you have that value for the kinetic energy at that point, 35 joules. Now you should be able to see something here, that he did 35 joules of work to displace the spring 14.1 centimeters. That therefore is also the kinetic energy at the equilibrium. So he's showing you a calculation where you see how those two are equal. So the kinetic energy at equilibrium is the same as the potential energy at amplitude. So he goes on, so now we take kinetic energy, we also know that's equal to 1/2 mv squared, so the equation from module 8. So you're able to plug the numbers you now have into that, and you're able to determine, as you see, 2.5 meters per second is the speed of whatever the object is that's hanging from the spring at equilibrium. So again, those three equations give you everything you need to solve those kinds of problems. So he asked the second question. A 23 gram mass, so now you're given the mass, on a spring, you're given the value for K. If the spring is stretched 12.3 centimeters, so now you're given the displacement, and released, what will the mass's speed be when it is 8 centimeters from its equilibrium position? So in other words, it's going from 12.3 centimeters of displacement to 8 centimeters. So he's asking what's the mass's speed at 8.0 centimeters from its equilibrium position. Well, you start out with the potential energy equation. You have mass, you have the value of K, and you have displacement. Your displacement here that you're looking for is 8 centimeters. So you're able to calculate the potential energy because you plug that into the P equals 1/2 times K times the displacement squared. You have the numbers for that, and you come up with a potential energy of 0.15 joules at that point of displacement. So the question is, and the question you need to answer is, what's the kinetic energy at that point? It's only by knowing that you can calculate the speed. So we do know that kinetic energy, as he shows you on 337, kinetic energy plus potential energy equals 1/2 Ka squared, which we just showed you up above, which is also the total energy. So you're able to plug in the 0.15 joules for potential energy, and you plug in your value for K and your displacement, and you can come up with the kinetic energy of 0.20 joules. Now again, you use the same equation from module 8. Kinetic energy equals 1/2 times mass times v squared. So now you have the kinetic energy, 0.20 joules. equals 1/2 times 0.23 kilograms times v squared. So again, you plug those numbers in and you solve for v, and you get 4.2 meters per second. Now, this looks fairly involved, but I hope you can see that, again, the mathematical manipulation is not that difficult. As always, you have to see what values the problem gives you, what it's asking for, and in your mind think through how are we going to achieve that particular answer. So now let's go to the next page where we have the on your own problems, and I'm going to have some pauses in this, and for the most part I'm just going to wait 2 or 3 minutes while you're working through the problem, and then I'll try to walk it through. I'll try to point some things out with the problem initially and help you get started with it, but then I'll wait about 2 or 3 minutes and then I'll start walking through answering the problem. So the first on your own problem here, 10.6. How much work is required to stretch a strong spring? So it's going to have a high K value. And look at that, 3,412 newtons per meter. So how much work is required to stretch a strong spring 34.5 centimeters? Now think about 34 centimeters. That's a little over a foot. So again, 100 centimeters in a meter, so it's approximately a little over a foot. It's quite a lot of stretch for a spring. So again, you're given the K value and you're given the displacement. So you should be able to calculate potential energy. So that's where you start. Okay? So start doing calculations. Again, you need equation 1012, basically, from 335 to do that. This is a pretty simple one. I need to remember that you need to convert the centimeters to meters. Okay, hopefully that was not a difficult problem. You're simply plugging the two values you're given into the simple equation, potential energy equals 1/2 times K times the displacement squared. And if you work the units right, then it should come out as 203 joules. Okay? Again, you can check that in the answers to on your own in the back of the module. So 10.7. A 61.2 kilogram mass is placed on a spring and set into simple harmonic motion by pulling it 23.1 centimeters from its equilibrium position. So again, this is quite a bit more displacement than what you did in your experiment. If the maximum speed of the mass is 3.4 meters per second, what is the spring constant? So you're given a couple of very important numbers here. The first one is that you can calculate the kinetic energy at its maximum speed. So the kinetic energy, which would end up being at equilibrium, and so it's the total energy as well, because potential energy at that point will be zero. So you take kinetic energy equals 1/2 times mass times v squared. That will give you the kinetic energy. So get started with that one. But you have to take another step in order to get to the answer of what's the value for K. Sorry, I didn't think to get any Jeopardy background music for this. That probably would have been appropriate. Well, maybe Sue can speed this up if you're already done. Um, but essentially what you're doing here, again, as I told you, to get the kinetic energy, you're given the variables that you need for that. You're given the mass and you're given the maximum speed. So when you calculate that, you're given the kinetic energy, which is also the total energy at that point, at maximum speed. So you're able to set that now, the answer was 350 joules. So you're able to set 350 joules now equal to the equation that you would calculate for potential energy at amplitude, because now that represents the total energy at amplitude. So 350 joules will equal 1/2 times K times the amplitude squared. So the amplitude again is 23.1 centimeters. You're given the full distance. So now you just plug those numbers into that equation, and you'll be able to calculate the value for K. Well, hopefully you're starting to see how to work with these equations and work and be familiar enough with it and see that these problems are not difficult. You're usually given enough information to calculate either the kinetic energy or the potential energy, and then assign and then you can solve for speed or even mass if that's not given to you and the speed is given to you. Or K is given to you, or you can solve for K. So there's lots of different ways you can go with these problems. So 10.8, a 54 gram mass, so again, that's going to be 0.054 kilograms, is placed on a spring, K equals 15 newtons per meter. If it is displaced 5 centimeters from its equilibrium position, how fast will it be traveling when it's only 2.5 centimeters away from the equilibrium? Okay, so you can calculate a number of things from this. You're given the value of K. You're given the displacement, both a total and a partial. And with the total displacement, you're able, from that, with the value of K, you're able to generate the potential energy, which at that point is the total energy. So that's how you get started with it. So I'll give you another minute. Okay, so how you doing? You should have been able to calculate that the potential energy at amplitude is, I think it's 0.0047 joules. And using that and putting that into the equation of kinetic plus potential energy equals the total, which you can use that as the total energy as well. You can solve for kinetic energy as 0.014 joules. And then using that, you use the 1/2 mv squared equation for kinetic energy. You're able to solve for V, and that's 0.72 meters per second. So again, what you did here is that you were given initially a value of K and the amplitude. So from that, you can calculate the potential energy, which at amplitude is also the total energy. So potential plus kinetic at the 2.5 is going to be equal to that energy, to the number you calculated for potential energy. And then it's simply a matter of putting in the amplitude that you have there and solving for 2.5 centimeters and solving with that, because you have everything that you need to solve that at that point. So hopefully that again is clear, and you can see how those are manipulated. That can be a little confusing, but again, I hope you see the mathematics is not terribly difficult. The last section of the module talks about pendulums, and I'll leave you to read and hopefully study 338, 339, 340. You're given an equation eventually on 341, equation 1020. So the period equals 2 times pi times the square root of L over G. G is the acceleration due to gravity, and L represents the length of the string on the pendulum. So if you've got something going back and forth, the length is from here to here. So you've got something at the bottom, and L then is the length of the string, okay, of the pendulum. So again, this is fairly simple mathematics, and you can walk through how he derived everything. There is a statement in bold on 340: when the angle of displacement for a simple pendulum is small, less than about 20 degrees, the pendulum exhibits simple harmonic motion. So again, it has to be a small displacement to one side or the other, and then you can have just a simple harmonic motion, and you can do various calculations using that. Okay, so you get the equation on top of 341, equation 1020, and the example is about the length of a grandfather clock, of a standard grandfather clock. Now he explains some things about this when talking about a standard grandfather clock. It goes back and forth every time it goes one way, that's a second, and then back is a second. So its total period is 2 seconds. And because of the force of gravity, then the length of the pendulum in a standard grandfather clock is a set distance. And so he's asking us to calculate what that is. So he gives you the equation, t equals 2 pi times the square root of L over G. You plug in the variables that you have, you're able to solve for L, and that comes out to 0.99 meters. And he says for a standard grandfather clock, that's the length of the pendulum. But you can have a clock with a pendulum that's shorter. It's just that it's not going to have the same displacement in order to be able to keep time properly. The period may, if it's shorter, will have to be less than 2 seconds or 1 second. And he goes on a long discussion on 342 about keeping time today and how we do that. And he talks about the atomic clock and the quartz clock and those sorts of things. And it gets pretty minute in the discussion and the details that are included. But again, as he says in the text, you don't really need to know that, but there is an atomic clock at the National Institute of Standards and Technology in Boulder, Colorado, that technically keeps time for everybody. And they say it will lose a second about every 20 million years. So for the most part, I guess that's pretty accurate. All right, the on your own questions, I want to get through these fairly quickly and just at least go through at least some of the review questions with you. You'll have Mrs. Bohlin will hand out the answers to all of those before you leave today. Those will be copied and handed out to you. So, on your own, 10.9, what's the period of a pendulum whose length is 2.5 feet? Again, you're given the length, and you're simply asked for the period. You can plug that number into equation 1020 and just calculate the answer. I didn't even write that one down. That should be simple enough to carry out. Again, yeah, that's just 1.8 seconds. Simple plugging into the equation. And essentially 10.10 is the same way, only this time you're asked, you're given the period and you're asked to calculate the length. So you're just solving for one of the other two variables in the equation. And let's see, I'll give you a few seconds to try to work that through. Should be pretty simple. Baylor's here with me, just so you know. Want to say hi, Baylor? Not really. Okay. Okay, the answer for that one is 0.050 meters or 5 centimeters. So, again, those problems, as I said, are pretty basic. Shouldn't be much of a challenge for you. Okay, I can't stop to ask for questions, so we're just going to move on. If you need to pause this, I won't be going on for a full 55 minutes in case Mrs. Bohlin does have to pause this at one time or another, especially with waiting for calculations and such. So I'll end a little bit early. But look at the review questions, 349. And some of these, as you know, are simply asking questions that help you make sure you understand some of the basic principles. Number one, a mass spring system is displaced from equilibrium by 5 centimeters and its period of motion is determined to be 3.0 seconds. What will the period be if it's displaced from equilibrium by 15.0 centimeters? That relates directly to one of the experiments you did, and your answer should be fairly quickly what? Well, yeah, it's 3 seconds. It doesn't change. So the displacement can change, but the period doesn't change. Okay, the period of motion. Number two, what is the definition of a restoring force? Now just think about the name, restoring force. Now there's when you stretch the spring, okay, the restoring force is going to be what pulls it back. So another way to state that is that the force directed toward equilibrium. So equilibrium is up in this case, so it's a force directed towards equilibrium, the equilibrium position. Okay, and there's a more technical way, but that's the basic understanding of it. A mass spring system number 3 is displaced from equilibrium by 34.1 centimeters. What's the amplitude of its motion? That's not difficult. Okay, it's 34.1 centimeters. In fact, he just didn't call it amplitude, but that's what it is. He displaced it 34.1 centimeters. That, by definition, is then the amplitude. 4. What condition must be met in order for a system to exhibit simple harmonic motion? So again, simple harmonic motion is a concept he's expecting you to have a good understanding of. Well, it's a restoring force that's linearly proportional and opposite to displacement. So, in order for simple harmonic motion, the restoring force has to be proportional to, but opposite to the direction of displacement. So this is displacement, and the restoring force, in order to be simple harmonic, has to be perpendicular and straight back to, opposite to, linearly proportional. That's the phrase. It's linearly proportional, not perpendicular. It's linearly proportional and opposite to the force of displacement. So 5, in a mass spring system, where does the system reach its maximum speed? If you answered equilibrium, that's correct. When at equilibrium, it's at maximum speed. In a mass spring system, where is the mass subjected to the greatest force? Well, at amplitude, because that's where the acceleration is greatest. So you stretch out the spring, and so here at this point, this is where the greatest force is being subjected on the spring to pull back. That's the restoring force. Number 7, a mass spring system, where does the system reach its maximum potential energy? Well, that's at amplitude. So that maximum potential energy is right here. Wherever I stop, that's the maximum. That's maximum potential energy. Okay. Um, 8, a heavy box is dropped on a spring and the maximum compression of the spring is measured before the spring pushes the box back up. If the box is dropped from a greater height, what will happen to the maximum compression of the spring? Think through, okay, from a particular height, it's dropped on the spring and it gets compressed, say, from here to here. So if you drop the box from an even higher height when it contacts the spring, will the compression be greater or less than the first time? And the answer is yeah, it's going to be greater than. So the spring is going to be compacted even more because the force that's generated from a higher height, because of the acceleration due to gravity, the box is moving faster, and so it's the same mass, but it's a greater speed, so there's greater force. Okay. Number 9, which of the following situations will result in simple harmonic motion after the mass is released? So you've got a pendulum and you've displaced it, and one of the pictures shows that the displacement. Let's see, let me put something like this together real quick. Let's say the pendulum moved out here, and then the pendulum moved kind of out here. So which one of these, this one or this one, is more likely to give periodic harmonic motion? Well, it's the one that's close. It's not displaced very far, something that's within that 20-degree limit that they gave you in the definition. So it'd be A. That's the one that's probably less than 20 degrees, and it will be able to produce simple harmonic motion. I'm sitting here with our front windows in front of us, and Baylor is sitting down with his snout on the windowsill, just watching the squirrels up in the tree. Number 10, if a pendulum's period is measured on Earth and on the Moon, where will its period be the longest? Well, it's going to be where gravity is less. So on the Moon, the period will be longer because there's less force pulling it down than there is on Earth. Okay. So let's take a look at the equation for that. So for period, you have the force of gravity in the equation on equation 1020, page 341. So if the number for G is less, then if the period is the same, then L is going to have to be greater, okay, in order to get that to work out right. So when G goes down because of lesser gravity, L has to go up to keep the period the same. Okay? No, that's not the way that works. You probably already caught that. What you were able to see is that the question was asked, the period was measured on both, okay? So apparently the length is the same, so the length of the pendulum is the same, and if the value of G is decreased, well, the period has to go up. So that's how that works. So the distance is the same, so L is the same, G varies. When G goes down, since it's in the denominator, the value of T has to go up. Okay. All right, so practice problems. We won't get quite as far into these, perhaps, but you'll have the solutions and the answers for all of these. Number 1, a hanging scale uses the fact that the length a spring stretches is directly proportional to the weight of the object suspended from it. So that's how that kind of scale works. If a 10-Newton bag of vegetables, that's a lot of vegetables, causes the spring to stretch 5.6 centimeters, what is the spring constant on the scale? And this is just applying the equation of force, which is newtons, equals negative k times the displacement. So you simply put those in there. You put in your force, the newtons, you put in your displacement, and you're able to calculate the value of k for the spring. The answer there is 180 newtons times meter. So in the second equation, second question, it's really applying, you have an added step here. A dart gun consists of a horizontal spring, and it gives you the value for K, that is compressed 4.3 centimeters. So the spring is compressed. Okay, so the spring is kept, and then in order to launch the dart, you have to push the spring back, okay, for it to push out again. All right, and so you give the value of K, it's compressed 4.3 centimeters when the gun is cocked. What's the initial acceleration of a 75-gram dart when the gun is fired? So initially, again, you need to use the F equals negative K times the displacement, and you calculate the force of negative 2.2 newtons. In order to calculate the calculation, then you just have to take the force equals mass times acceleration equation. You're given the mass of the dart. You now have the force of 2.2 newtons. You plug those two into it, and you get an acceleration of, I think it's minus 29 meters per second squared. Again, I hope you're seeing that similar to the last module, the calculations here are fairly basic, fairly simple, and hope you'll be able to work these things out pretty easily and get to some good answers. Next one's a little different. It says a 50.0 gram puppet bounces on the end of a loose spring. So it has a small K value, spring constant, the 1.5 newtons per meter. What is the period of its motion? Well, we have a pretty basic equation for that, and we're given the mass, and we're given the force, the K value. So you're using the T equals 2 pi times the square root of the mass divided by the K value. So, and you get the answer for 1.1 seconds. So you look at the period equation, which is the earlier one, not the one that we used. So that's on page 330. That's equation 1011. So the period equals 2 times pi times the square root of the mass divided by K. So this problem gives you K, it gives you the mass, and you're able to initially calculate the force using delta K, using the F equals minus K times delta X, and then you plug the answer into the force equals mass times acceleration. You solve for acceleration, and I think it's minus 29 meters per second squared, or 2.9. I'm not reading my note really well there, but again, you'll have the answers for you before you leave today. Okay, maybe let's look at one more here, and if this lets you out a little early, that's fine. That's not a problem. I'm sure you won't complain. Let's see, maybe one or two more. We'll take a sample of some of the other types of problems. Let's move down to 5. It says a mass on a spring, and it gives you the K value, vibrates back and forth with a period of 1.1 seconds. What is the object's mass? So again, you should be able to plug that into the same equation you just used above. You have the value for K. You have the period, so T equals 1.1 seconds, and it wants you to solve for the object's mass. So you take that T equals 2 pi times the square root of mass over K, and you just solve for M. Oh, you're given the mass, sorry, you're solving for, you're solving for M, which is 0.92 kilograms. Okay. Maybe just one more, number 7, or maybe just number 6, a little simpler. How much work does it take to compress a spring with a K value of 78.1 newtons per meter? You're displacing it 51.1 centimeters. And again, that's the using the potential energy equals 1/2 times K times displacement squared. And you just calculate that through and you get a force of 10.2 joules. So again, hopefully you can see that finding the right equation and using it is not a difficult task with this module. And I think we'll call that quits for today. And I believe this should be Thursday. Let me see, the 17th. I think that's correct. And 17th. And your test for module 10 will be next Tuesday. So work through all your problems and the practice problems, review questions, and have those ready to hand in. And you have the solution. So again, test yourself. Since you have the test yourself to go through, try to work them out on your own before you look at the answers, and that's obviously the best way to learn. So good luck on the test on Tuesday. Thank you.